it's a funny movie. It's not really.
I will take your word for it.
I mean, I'm an adult, so I can watch it. I am 18. You're 18.
You do what you're going to do at the time that you have available to you. Okay, here we go. So, I told you guys prior to the absences that should you choose to be away on any given day, the videos would be posted, and I'd expect you to go through them. So I will just leave that video for you to go through, and we're going to move on to Lesson 8. Today we're going to do Lesson 8, and we're going to start Lesson 1 of magnetism. It's going to be great. Because this is the last lesson out of electrostatics, and we're just tossing all this on the test next week, 1 week from today. Yeah, here we go. Well, this is just one lesson. This is the last lesson of this unit. Yes, this is lesson 8 is the last lesson of electrostatics. So, for parallel plates, the voltage is given by the battery or whatever power supply is present, and it varies directly with the distance between the plates. We've established this yesterday. So, because the plates are very, very large, there is a uniform distribution of voltage here. So, let's say there's a 5, again, for those of you who didn't watch the video, if there's 500 volts here and no volts here, so that's a large power supply, and there's a 5 millimeter gap, every millimeter is an increase of 100 volts going from 0 to 500. The uniform distribution. And the electric field we've established, so watch the video, is constant between these plates, constant everywhere. It doesn't matter where you are between those plates. We recall that for a test charge placed at a point whose voltage is known, we can find the potential energy using an equation that we had derived, not yesterday, but the day before. The potential energy is equal to the charge that you've placed there times the voltage at that area. We also know, I'll bring it back here because I think I've written it down before. Yeah, we wrote it down before. That work is change in potential energy. Well, change in energy, and in this case, we have potential energy. So whatever work is being done here is going to equal the charge times the change in voltage, which is going to be a useful expression for us here. So I've got a situation of this. I want to find the work done by an external agent that moves a positive 2 microcoulomb charge from the negative plate to the positive plate, assuming the charge begins and ends at rest. So this is a positively charged object. The positive charge wants to do what? Based on what we've drawn here, or what is drawn here for us. What does the charge want to do? It wants to stay where it is. Why does it want to stay where it is, Joseph? Well, it's grounded here. It's 0. But this is big positive. So big positive is going to have an electric field that goes this way. And the positive charge is going to want to follow those lines, get repelled by that positive plate. So if we wanted to take that positive charge and slide it up, we would have to do work somehow to make that happen. You grab your teeny tiny tweezers and you shove it into the electric field and you raise the positively charged object. However it is you're going to do that. We want to find the work done. Work done is a force times a distance, assuming that the force is constant throughout. Or work is equal to a change in potential energy. You can use either one of these things to tackle some of these kinds of problems. The energy one is the easiest one to deal with, and that's the point that I'm trying to make here. So we can set it up the same way we did before. Energy initial plus work equals energy final. We also don't know how far these plates are, so we can't use work equals force times distance. So looking at where this thing is, it may or may not have some potential energy at the beginning. We're going to do some work, and there's some potential energy at the end. Potential energy initial is given by Q times the voltage initial. V stands for voltage, not velocity at this point. Times Q voltage final. What voltage is this thing starting at? Starts at 0, so there's no initial voltage. So then the work done is just going to be my charge, 2.5 times 10 to the negative 6, times my final voltage of 120 volts. How much work was done? 3 times 10 to the negative 4 joules. So not a lot of work, relatively speaking. So let's make this more interesting. Flip the page. The density of interesting is not uniform. There are spikes of interesting. We have to find the next spike. Here we go, example 2. We want to find the speed of an electron beam if it is accelerated by 125 volts. There is no external agent, so system energy is conserved. If system energy is conserved, what is the implication in that? There is no work being done. Work equals 0. So I've got negative 125 volts going to 0 volts. Again, if we looked at dang it, I lost it. It was there. Oh, right. Yep. We're going back again. Here we go. If we remember what we're concerned about as far as the electric fields go, electric field and what's going on in here, we're concerned with the change in the voltage. Yes? So it doesn't matter if this is negative 125 and 0. As long as the difference from plate 1 to plate 2 remains the same, we can shuffle that voltage like a big slider. So this could say 125 and 0, or I could make this thing 0. I added 125 volts here, so I could add 125 volts here. So by making this 0, I could make this thing positive 125, and the result would be the same. This is a negatively charged object at a negative voltage. It's going to repel here. Or if I had a positive 125 volts here with a negative charge here, this guy's going to be attracted to this, and the acceleration is still going to happen. It doesn't matter which or where the voltage is located. It's all about the difference between them, and as long as that relative difference remains the same, we're good. You wanted to make this thing positive 125 and this one, sorry, like 250 and 125? No. This would be, 125 and 250?
Yes.
This voltage would still be larger. There would still be more of an attraction for that guy because the electric field is uniform throughout. It doesn't matter how close this guy is to any of either of the plates. And it's the electric field that's impacting the speed of this thing. So again, as long as the relative difference remains the same, it doesn't matter what these values are. So there's 2 ways we could set this thing up. We could theoretically set this thing up using dynamics, and then we have a force that creates an acceleration. We could use kinematics to use the acceleration to find the final velocity of that particle. There is one reason we cannot do that. We don't know the distance between the plates, and why is that necessary, Ashton?
I was going to say most of these require a formula, and then if you go back or whatever. Yeah, I don't know. I was just going to say, yeah, the kinematics formulas all need that, and you don't have time either. So.
We don't necessarily need time, but that distance is absolutely necessary. Because we don't know d. And the forces, the dynamics route for this requires these 2 formulas. Electric force equals Q times the electric field strength, and electric field strength is equal to the change in voltage divided by the distance between the plates. We don't know the distance, we can't use dynamics, we have to use energy. So, using energy to find the work. At the beginning, this thing has potential energy because I do have some voltage here, and I've got no voltage here. And voltage is given by Q times V. There is no work because we're told that system energy is conserved. What kind of energy exists at the end? It's kinetic. If instead of negative 125 and 0, I'd use 0 and positive 125 here, how would that have changed this setup? So let's just draw this here. What would happen if I had done energy initial plus work equals energy final using the green values here instead? Does it? VI equals 0.
Oh, yeah.
What kind of energy is present at the beginning? At 0 voltage, potential energy is given by QV. No voltage means no potential energy here. So there'd be no initial energy using these green values here. Plus no work equals what kind, using these green values now, if I have a voltage over here, what must I have at this point? I'd have to have kinetic because there's a velocity, and I'd have to have a potential energy expression. Yes, one of them is negative. Why is it negative? Well, and when we're dealing with the energies, we do include the sign on the charge, which would make this expression negative, which when I added it over would make that expression positive. Because, so I'd have 0 equals half mv squared plus qv. That q is negative. That v is positive, which would make this term negative. So then I'd add it over and I'd get kinetic energy is equal to some positive amount of energy. It would still work. Because what we're going to do over here is we're going to have qv equals half mv squared. Big V is voltage, little v is velocity. You have to use the context in which they're provided to make sure you keep those things straight. When we're dealing with energies, we do include the signs on the charge because energy is not a vector. So using the black values, it's an electron, so the charge on an electron is negative 1.6 times 10 to the negative 19. And using the black values, what's the voltage? Negative 125. So the negative times a negative here is going to give me a positive value, which is what we want because it has to be positive if it's going to give us a velocity at the end here. Yes. Because voltage is potential energy per charge. And if energy is a scalar, voltage has to be. So we've got half times the mass of an electron, which is 9.11 times 10 to the negative 31 velocity squared, which gives us a final velocity of what? 6.6 times 10 to the, thank you, which is 2% the speed of light. Oh, it's incredibly fast, but still slow enough to be measurable. Okay, so as you can see in the above calculation, when a particle is accelerated from rest by voltage, there's a simple equation here. Because there's no external work being done, it's typically, depending on how we set this thing up, it's going to end up looking like this. PE equals KE, assuming you reason it through properly. We must take care in this equation not to confuse the V in voltage with the speed V. It's going to end up looking like this. If you set it up properly, you're going to get voltage here and velocity here. Context is important. These are good, but there are better. Let's go bigger. Ooh, there's some good stuff coming up. Okay. So, an electron already moving at a 5 times 10 to the 5, at 5 times 10 to the 5 meters per second enters a set of accelerating plates. We want to find the speed when it leaves the plates. We can do that. We know what the distance is between the plates. We know what the voltage difference is between the plates. So we've got options here. Should you be given this on a final exam or a test coming up or whatever, I don't necessarily care how you go about solving these things, assuming that you use the appropriate tools given the information. Because we have everything, you could use dynamics to find the acceleration, and kinematics then for VF. That is an option, should you choose. But for the sake of what we're about to do, I am going to show you how to do this problem using energy. So we've got energy initial plus work equals energy final. What energies are present where? So I've got kinetic energy here and I've got kinetic energy here. Different expressions for kinetic energy. Well, same expression but different values because I've got a VI accelerating into a VF. But I've got kinetic energy at both. So I'll have a KE here equals a KE here. What else do I have? Currently, the way it's written, we have a potential here, and we have a potential here. Okay? But I argued with you earlier that it's not about what the individual potentials are, it's about the difference, not the total, but the difference between them. So as long as the difference remains the same, the relative difference remains the same, we could rejig these numbers to make our expression look a little bit nicer. Because right now, as it's written, Blake, you're right. We've got a potential energy here and a potential energy here. So I've got PE plus KE equals KE plus PE. But yeah, if I take this 100 and 600 and I subtract 100 from both of them, that's going to make this guy what? And then this guy's going to be 401. Nice. Okay. The relative difference is the same because 100 to 600 is 500 volts. 0 to 500 is 500 volts. Okay. So to make our life easier, we can do this shift and it's not going to change anything. Except maybe the engineering required to make this happen. So now with this shift, I've got kinetic energy here. That's it. And I've got kinetic energy here and potential energy here. So I've got KE initial, KE final, PE final. So KE initial is given to us by, it's being accelerated by the plates, so there's no work being done. No external force. But half MV initial squared is going to equal 1/2 MV final squared plus Q VF. The big VF is, this is voltage now. You got to keep this straight. So if I fill this thing out now, I'm going to jump all the way to the left-hand side here because it's going to start taking up some space. 1/2 9.11 times 10 to the negative 31 is my electron mass. It can't. Yes, good point. Yes, no, Ashton, I'm glad you said it. I cannot cancel the mass because the mass does not show up in this term. And I guarantee you a classmate or yourself would have tried. Initial velocity we're given is 5 times 10 to the 5. We're going to square that, and that's going to equal 1/2 9.11 times 10 to the negative 31 VF squared, which is what we want, plus, it's an electron, so it's negative. It's an electron, and we're dealing with energy, so it's negative 1.6 times 10 to the negative 19 times 500 volts. So what's VF? You have more digits than that?
Oh, yeah.
Go.
13,260,000.
Can someone verify? Same answer? Sweet. And that makes sense. We started with a kinetic energy. It's an electron moving towards a positive voltage. So there's going to be a positive acceleration here. That negative is going to be connected to this positive plate. So I've got this negative on the right-hand side that's going to get added over, increasing the kinetic energy, giving us that speed there. An application, yes, Nathan. 500 is the voltage of the plate at the end. Yeah, we shifted it. An application of this is a device called a cathode ray tube. There are varying degrees of simplicity in a cathode ray tube. The simplest cathode ray tube is a beam of electrons being accelerated by one set of plates, then deflected by another set of plates that hits a fluorescent screen, causing it to glow. Application of a cathode ray tube, anybody? Nathan? Nope. Nope. What kind of TV?
Like a big brick. It's like a really big box. It's whatever one we had to use. That's it. Yeah, that one.
Oh, this television is a CRT TV. The reason it is called a CRT TV is because it's got a more complex version of one of these. There are two ways to set up, or a couple ways to set up a cathode ray tube. One is by using magnetic fields, which we're going to look at. The simplest one is use electric fields. So what you've got, sorry? Part of the reason, yeah, there's static on here. Because there's a big tube back here that is accelerating electrons through a set of plates like this. And then there's a set of plates like this. There's actually two. One top and bottom, one left and right. The top and bottom can create a deflection which way? Up and down. So this is positive. This electron is going to swing up this way, because it's ultimately attracted here, and then either this is ground or negative, it's going to be repelled from here. But you can vary this voltage. You flip this. It's causing a downward deflection. Plates left and right are going to make this electron do what? Go left or right. So now, yeah. Or if you even watch it through if you get your phones out, you watch it through a screen. I'll put it on the ground over here. I mean, and the reason that these things are so heavy is because it's not the simplest cathode ray tube. It's actually a small that uses a huge friggin' magnet. Which we'll talk about. It's also really thick glass. You ever find yourself in the bush with a television? Careful what you do with it. I shot one of these once. Oh, yeah. The bullet came back. Nope. Fast enough. Well, it was shotgun pellets. Thank you back. We need. In. Plug something in. Well, let's do that later. I thought we'd get some color here at least. But yeah, I mean, you can feel it.
You can hear it too.
Yeah. Feel my arm.
I remember.
So you've got. I will plug something in here later so you guys can actually see it, but you can see it streaming across the screen. The refresh rate, these things refresh at 60 hertz. So 60 times every second, you get these lines going down the screen, refreshing the image. And basically all that means is the cathode ray tube is changing the voltages, left, right, up, and down, causing the electron. It would make sense if it started top left and then just across and down, remaking your image 60 times a second. That is an application.
Where do they end up? They don't shoot out stuff. Yeah.
What do you mean?
I thought with the
They hit the fluorescent screen.
Okay.
So the reason they glow, the reason that you can see light being emitted, is because that fluorescent screen. It comes back to what Hannah mentioned a couple days ago, when we were up in the lab. It's the excited electrons drop into an orbit. Well, on a screen that fluoresces, they're impacting, and their energy, they fall into an orbit. It's behind the glass. It's behind the glass. So, an application of this. Let's do the math. Flip the page. There's one big tube. Yep.
I guess it's not just one electron at a time.
Oh, it's a whole stream. It's a constant stream. It's like a hose. Yes, it's a constant stream of these things. Yeah. Okay, so we've got a cathode ray tube, functionally an electron gun. If you think back to Science 9, pretty sure Science 9, maybe middle school, but Science 9, the cathode ray tube was an important tool in the development of our current model of the atom. J.J. Thomson, again, my favorite of the guys. J.J. Thomson is did a lot of his work with this, analyzing electrons. So here we go. We've got this set up. We've got 1200 volt difference here, a 750 volt difference here, and a fluorescent screen over here. We want to figure out what's going on. So basically let's analyze this. What's going to happen here to the electron? Well, if it doesn't matter what side is which. No, you know which side it has to be, Nathan, because if one side is, if it's wrong, then nothing's going to happen because the thing's not going to move. So let's assume we want this thing to move. What's going to happen? The purpose of these plates is to do what? Accelerate the electron, yeah. These plates are going to deflect it. If that's the negative, that's the positive. Which way is the deflection going to be? I can't handle that high pitch noise. Can anyone else hear that? Yeah. Oh. Hate that sound. Electric field here is going to cause the electron to do what? Deflect up. As soon as the electron leaves this field, it is no longer experiencing a force. What's the electron going to do? The up and down force here had no bearing on the left and right acceleration. Here, left and right acceleration is going to give it an initial velocity. Sorry, it's going to give it a final velocity. That final velocity is going to remain because it's going to the right. This force has no bearing on that velocity component. So it's going to have that horizontal velocity the entire time. This is going to cause it to deflect up, which is giving it an initial velocity, or it's giving it a velocity upwards, a component of a velocity upwards. As soon as it leaves this force, there is no longer any forces acting on that electron. There's no forces acting on an object in motion. That object is going to continue in motion until it is acted on by another force. Newton's laws. If you were here yesterday, you'd see that the force of gravity was... Did you watch the video? You should watch the video. We analyzed why gravity is totally ignorable. Because it's incredibly small. Like 10 to the negative 47 small. So it's going to move at a... what's the path going to look like? It's going to be a straight line. Up here somewhere. So let's do it. Who closed my door? Whatever. Let's do it. A. We're going to find the speed of the electron beam. Now, a question like this is not going to be posed as A, B, C, D, E. The question will be posed like, what is the vertical displacement of the beam when it leaves the CRT? Or if I'm really nasty, I could give you the distance from here to here, and I could tell you where on this screen does the electron hit. I'm not going to, but I could.
Oh, it fronts the glass.
Sorry?
Oh, that's supposed to be the glass.
Yes, and this is the fluorescent,
Eye.
the fluorescent screen, yeah. So it's going to hit on here somewhere. If I gave you this distance, you could tell, the horizontal distance here, you could tell me exactly where on that screen this thing hits. So to do that, you've got to take yourself through these steps. This thing's going to cause the electron to accelerate. This thing is going to cause it to deflect up or down. And then once it leaves this section, it's going to travel on whatever straight path it was on before, using the components of velocity that these two things give it. So the first thing we got to do is figure out what this voltage is. Sorry, what this velocity is due to this voltage. So the easiest way to do that, we don't know the distance between these plates, so we're going to use energy. There's no work being done. So we're going to have the potential energy initial is going to equal the kinetic energy finally. So we've got QV equals half mv squared Nathan, the only way for this to work is if what voltage do we have here initially? You want it to accelerate this electron away from it. So this is going to be negative 1200, and this is going to be 0. Good. So negative 1.6 times 10 to the negative 19 times negative 1200 equals 1/2 9.11 times 10 to the negative 31 velocity squared. We'll call it Vx final. Again, as long as they're different, the difference has to be 1200. I could have made this negative 600 and 600, but then I'd have a potential energy term over here. I want to set this up as simply as possible. So having a potential energy equal a kinetic energy, potential equals kinetic means that's got to be where the voltage is. If that's an electron, that's got to be negative voltage. Yeah, right. Yes. Because at this point, it's going to leave the electric field. So what is my x component of velocity finally?
20 million.
Anyone verify that? Blake's good. Okay. So we figured out what the horizontal velocity component is, and because there are no forces acting horizontally in this thing, that's going to remain constant throughout. Do you have to worry about air resistance on an electron? No, because air is smaller than the oxygen. Sorry, the electron is smaller than any particle that exists in the air around it. We're not dealing with air resistance anymore. If it hits a molecule, if there is air in here, it's not, it's a vacuum tube, which is why the glass on the front of these TVs is so thick. If there was air inside here, the electron would hit it and it would get absorbed by the molecule. So we're told we need, the next piece to this is we're going to have this electron. It's going to enter traveling that way. In order to find the deflection here, we need to find a few things. We need to find the force produced in here for the electron. That's going to create an acceleration. Then we're going to have to figure out how long the electron is in this gap for, because that's going to tell us how long this thing is going to be accelerating for. That'll tell us what the vertical component of velocity is as it leaves the end. Okay. The first thing we're going to do is we're going to find the vertical acceleration of the beam in the deflecting plates. So B. We know that as soon as this thing enters this field, it's going to have a force in that direction. That force is going to produce an acceleration. So F net equals ma. I have hopefully shown you, well, those of you who watched the video were here yesterday, I hope I've convinced you that we can ignore gravity. The rest of you just have to take our word for it. So the only force acting on the electron is the force due to the electric field. The expression for that is Fe equals QE. QV, rather. No, QE, yeah.
No, QE and then
QV is potential. So force electric equals Ma, and Fe equals Q times E. So QE equals Ma we don't know what E is. How do we find E?
delta V voltage over.
Yeah. In a set of parallel plates, the electric field is given by the change in voltage divided by the distance. Now the distance here is which distance? Yeah, the separation of the plates. This distance here. So we're going to get Q delta V over D equals a mass times an acceleration. So my acceleration in the y direction is going to be given by this expression here. Q delta V over MD. Now I can fill this thing in. The charge on my electron is, again, now we're dealing with forces. So we've already used the direction here. So I do not need to include the charge on the electron. Sorry, I don't need to include the polarity of the charge on the electron. So I've got 1.6 times 10 to the negative 19. The change in voltage between those two plates is 750 volts. The mass of the electron is 9.11 times 10 to the negative 31. And the distance between those plates is 0.02 meters. While you guys are calculating that, someone said something about radiation. Yeah, technically yes, because beta radiation is just a stream of electrons. So if that thick glass doesn't exist at the front, yeah, you're just getting bathed in beta radiation. But thankfully, beta radiation is electrons. Electrons are really easy to absorb. So that thick glass at the front is also shielding you from being bathed in beta rays. Oh yeah.
Let's do it. See how long we survive.
But even in the air, like the electrons are going to start hitting air molecules. They're going to get it's important to recognize the shielding of different types of radiation. While you guys are calculating this, let me know when you got a value.
Yeah.
Oh, Ashton.
6.59 times 10 to the power of 15.
Can someone verify? Thank you, Abigail. Meters per second squared. So again, just a bit of an aside, we're dealing with radiation. We always, radiation is this buzzword. Radiation's bad. They use big pools of water to store like the used uranium rods. So once they're done with it, they just drop them to the bottom of a pool in these big barrels. The water is so good at absorbing the radiation that these things are emitting, a whole host of nasty stuff, that you could actually swim in the top 10 meters or so of water. They're fairly deep. But you could swim in the top chunk and not worried about what's going on underneath. The biggest concern would be the guards with guns that would shoot you as soon as you hit the water. But the radiation at the bottom, there would be no impact there. In fact, it goes so far as I was reading not that long ago. There was a diver, and divers have to go in and clean these pools, make sure everything at the bottom is still the way it's supposed to be. So they went down there. They found a piece of a material that had come from inside the reactor that wasn't supposed to be there. They don't know how long it had been there. So he grabbed it and put it in his his basket. So divers have lots of straps on them. He could have very easily just shoved it inside one of his straps, but he put it in the basket he was holding. Okay, the basket he was holding was this far from him instead of right next to his skin. This distance saved his life. Because if he'd strapped it in here, that thing was so radioactive, he would have gotten a lethal dose to his body. But because he's just carrying it in the basket, again, 1.5 feet away from him, he was totally fine. His hand experienced a dose of radiation that was not insignificant. But water is a phenomenal barrier for radiation. It's a great insulator for absorbing radiation, absolutely. So so as far as the TV is concerned, that inch thick glass at the front, almost an inch thick, is plenty. You don't have to worry about getting irradiated by your television. So we found an acceleration upwards. Back to this. The next thing we want to find is how long this beam is in this area for, because that's going to determine how much upward acceleration this thing gets. So to figure out how long that is, that's a relatively easy calculation. Let's do it down here. I want the time for this. T equals question mark. And the only thing that determines that time is what? It's going to use kinematics to find it, but what determines how long it's in there? Yeah, the horizontal speed, which we found already. Vx is 20,530,826 meters per second. Acceleration horizontally, 0. The distance this thing is traveling horizontally is 5 centimeters. So 0.05 meters. So I want to figure out how long it's in that gap for. This is just a T equals D over V, constant velocity kind of problem. My distance is 5 centimeters, so 0.05 meters. My velocity is 20,530,826. How long? Not very long.
8.44 times 10.
Someone verify. Okay, we're good? Okay. So now we can establish what's going on here. This guy is going to start to deflect upwards. And then once he leaves, he's going to have some vertical component of velocity. Vy final. We need to know what that value is. How fast is it going upwards now? So part D. Find the angle and speed at which it leaves the CRT. So we're going to find that Vy component there. Vy final is going to be what we're looking for. We know the acceleration in the y direction is, where'd that value go? 6.59 times 10 to the 15 meters per second squared. We know that the length of time it's in the tube is 2.44 times 10 to the negative 9 seconds. And the initial y velocity is our favorite number, 0. So Vy final equals Vy initial plus AT is the kinematic equation we're going to use there. That's gone. So Vy final is just going to be our acceleration, 6.59 times 10 to the 15, times our time, 2.44 times 10 to the negative 9, which is going to give us a final velocity in the y direction of what?
Oh yeah.
So Nathan, what was yours? So 1.6.
1604.
Hold slow down. 1.6.
I'm trying to figure out how many. 16 million.
Just one digit at a time, man.
1604.
Yep.
49.
49037. Can someone verify? I think something's wrong there.
How about the other one,
16,079,600. It should be 16 million, yeah, not 160 million. Meters per second. Okay. That 16 million is very close to the value I got. So that is the velocity in the y direction. We don't want the velocity in the y direction. We want the overall speed and direction of this thing. So we're going to have to combine its horizontal velocity of 20,530,826. Yeah, that's the horizontal component. Here's the vertical component, 16,079,600. To give us a particle that's actually going that way. With some speed v. So using Pythagoras, 20,530,826 squared plus 16,079,600 squared, square rooted, should give you a value somewhere in the neighborhood of 25 million. Well, that's in the neighborhood of 25 million. So you get 26 million.
78,000.
Yeah, when we're already talking, tens of millions, what's one more million? Meter per second. And rightfully so. And that angle is what? Exactly. So yes, let's call that thing 38 degrees. Cool. That's part D. We want part E. The vertical displacement of the beam when it leaves the CRT. This, though, right here, would be enough, if we knew this horizontal distance right here, to find out exactly where this thing hits. Because you know the angle at which it's leaving. You know how fast it's going horizontally, so you know how much time it's going to take to cover that distance between the leaving the plates and hitting the screen. And now you know what the final velocity upwards is. You could tell me exactly where this thing hits the screen with the information that we've been given. We would flatten it for the sake of the problem. So the last part here, question E says, find the vertical displacement of the beam when it leaves the CRT. The vertical displacement just means it came in at the middle and it rose while it was in there. How high is it risen? So we're also going to say that that's our dy. Well, that's easy to find. dy is what we're looking for. We've got a length of time. Where did it go? 2.44 times 10 to the negative 9 seconds. We have a Vy initial of 0, and we've got a Vy final of 16,079,600. That's in meters per second. That's in meters per second. So we can use a kinematic equation to find this. dy equals VIYT plus 1/2 AT squared. That's 0. So that's just going to equal 1/2. Oh, we have the acceleration here too. Where's the acceleration? We could use a whole bunch of different kinematic equations. 6.59 times 10 to the 15 meters per second squared. 1/2 times 6.59 times 10 to the 15 times 2.44 times 10 to the negative 9 squared. We could have used VF squared equals VI squared plus 2AD if we'd wanted to. We could have used D equals VI plus VF over 2 times T. Lots we could have done. What is the vertical displacement of our electron beam while it's in those plates? 0.0196. What are the units on that? Meters. So a more useful measurement is to take that 0.0196 meters and convert it to millimeters. Well, millimeters are centimeters. So that's going to be 1.96 centimeters. It deflected that far. For its size, that's substantial. But for all of our other ridiculous values, that's a nice number. That is a value that we can kind of connect with on a meaningful level. I cannot, no, I can't. I cannot fathom what 20 million meters per second feels like. And again, it's not about what that feels like, it's about what accelerating to that feels like. That's what's going to feel like something. Okay, here you go. I want you to play with this stuff. Give you some time. I want us to look at 1 to 4. I want us to look at 6 to 10. And I think I want us to do one more.
No way. 14 seems good. Did you guess it in your top one? Ready? All right. All right.
No, I'm not going to get you that. Yeah, we'll leave it there.
Like a little, I don't know.
A matrix.
Yeah.
It's linear algebra. It's a technique used for solving systems of linear equations. So like you know how to solve a 2-variable or even a 3-variable system. You isolate for one variable, substitute into the other one. You can do that with 3 variables, solve for 2, substitute it in, solve for 1, substitute it in, and now you've got that third equation with with 1 variable in it, and you work your way backwards. The matrix allows you to do that with as many as you want simultaneously, and it does it for matrix math will do it for you. It's beautiful. Yeah, the TIs or the Casios can do. So when you're solving 10, 15 variable systems of equations using matrix algebra, gets it done so fast. That is the beauty. But like everything else in math, you've got Abigail. Do you want a booklet? A blank paper. Oh, you want blank paper? Okay. But like everything else in math, it is a useful tool for physics, but it also has very deep implications all on its own, like so many other things in math do. Linear algebra was one of the hardest courses I took. Super useful, but as soon as you leave its usefulness, it gets crazy hard. Which is why, okay, if you ever have the option as a physics student to take linear algebra for engineers, as soon as they say a course is for engineers, they ignore all of the mechanics of why the math itself works, and they just teach the useful math. It's awesome. Yes. Any class listed as being for engineers just teaches you what's useful about it and ignores all of the, here's how we build the jackhammer. Screw that. I want to use the jackhammer. It can be. And I did a math degree, so I had to take the not for that. But if you're not taking a math degree, if you're just doing physics and chemistry or physics and engineering or whatever, any course listed as, but just so you're aware, any class listed as for engineering students is designed to give you the meat and potatoes of a technique that you can then use without having to really dig into the bedrock beneath it. And lots of the time, that's okay. That is what the difference is between those kinds of courses and how they're listed. But again, I did a math degree, so that was useless to me. Yeah, Grissom. Do I have a fork? Not for you, I don't. You can go ask the indigenous room. I know they have utensils. Plastic utensils. They're right next door. Yeah. It's Mrs. Fadden. You know Mrs. Fadden. Knock on the door. Hey, Mrs. Fadden, I forgot a fork with my lunch. Do you have a plastic fork I can steal?
We're all born with hands for a reason.
Okay. This is what I want you guys to work on. You're working set giver.